Okay, guys, so I know you're excited because you learned about logarithms. It's this whole new type of function that you never even knew existed. So I get that. And now you just want to know more, right? So we're going to talk about properties of logarithms today. And there's some really interesting properties of logarithms that, again, if you remember that logarithms are just exponents, it's not really that new because we know properties of exponents. So remember our properties of exponents. Let's remind ourselves. Of course, we already know this, but we're just going to remind ourselves that when we multiply two terms with like bases, we are going to add our exponents, right? When we divide two terms with like bases, we're going to subtract our exponents. What else do we know? We know lots of things. If I take a and I to the m and I raise it to the n, that's when you multiply your exponents together. We also know a to the 0 is 1. Those are kind of some stuff that you've been learning throughout your whole math experience. So now what we're going to look at is how do these properties right here really go and show us some properties of logarithms? Because again, logarithms are just exponents, right? Little refresher, what does log base 3 of 9 mean? That means to what do I raise 3 in order to get 9? That would be 2, right? Okay, so some properties of logarithms that are going to be important, and they're important in this section just because they're interesting. Well, I think so, but a lot of the things I think are interesting probably are not other people's idea of interesting. But really what they're going to do for us is they're going to help us solve equations involving logarithms. And that's really in mathematics, where I want to use that. I want to look at equations or applications. So there are a couple of rules. We're going to write these all down at once, and then I'm going to prove most of them to you, not perfectly. I'm not going to prove them to you perfectly, so don't freak out if it's not perfect, but and then we'll kind of put them all together and kind of do some examples with them. So the first rule is the product rule. So let's consider two positive numbers. Let m and n, capital M, capital N, be positive numbers. Okay. I guess I could say real numbers also in here, but for right now, let's just let them be positive numbers. And let a be any logarithmic base. So again, remember, what does a logarithmic base? It has to be positive, right? And it can't be 0. Okay, stay positive. Stay greater than 0, people. Stay greater than 0. All right, so let's let a be any logarithmic base. If that is true, then here's what I know. So again, let m and n be any positive number. Then I know that log base a of m times n. Let's look back up here, you guys. What happened when I multiplied two like bases? What do I do to their exponents? It becomes addition. That is what happens here with this property of logarithms. This is the product rule, and what happens is multiplication becomes addition with something a little bit different because we have a log in there. But another way to say that is that the logarithm of the product is the sum of the logarithms. So really quick, I want you to be able to sleep tonight. And if I don't prove this to you, you won't sleep tonight. You'll be like, but Sarah, how do I know that's actually true? You didn't prove it for me. So let me do a quick little proof of the product rule. So I'm going to define a couple things. And the way I'm going to define this, I'm going to define a couple new terms. I'm going to say, let's let x be log base a of m, and let's let y be log base a of n. Okay, so actually what I'm going to do is I'm going to kind of start off a little bit differently here, but if that's true, right, then if I use properties of logarithms, notice, you guys, that this a right here, remember, if I bring it across the equal sign, it's not the base of my exponent, but it stays a base. It's not the base of my logarithm. It stays a base, though it becomes the base for my exponent. Remember, x is an exponent. So the way I have this defined, look at what I'm saying here. I'm saying that a to the x equals m then. Well, this is implied by the definitions that I've given, x and y. And here this says that a to the y then equals m. Okay, so let's look at then what I can do with them. So thus, when you're doing a proof, thus always makes you sound super cool. Thus, therefore, or obviously is always a good one for a proof, or it follows, you know, those things that make us maybe seem smart, maybe. So let's take m times n, because look at what I'm doing up here. I know I'm taking m times n. So when I'm dealing with a proof, I want to maybe, you know, work with what I know I'm going to get eventually. So if I take m, what is m? It's a to the x. I multiply it times n. N is a to the y. What do I know with exponents? I know that I add exponents when I multiply like bases. Whoa, whoa. Settle down there, exponents. All right, so look at what I have. I have m times n equals a to the x plus y. So I'm going to do a little bit of work over here. So if I have m times n equals a to the x plus y, if I asked you, how do you rewrite this equation without a logarithm? People, look at what you're going to do. You're going to take the exponent across the equals sign, and it becomes the base for my logarithm. Ooh, it follows. It follows is a good one. Let's do it follows. It follows then, so it follows that, what do I have again? If I bring the a across the equals sign, it becomes the base of my exponent, or excuse me, base of my logarithm. I'm sorry, I keep getting those confused. Bring the a across the equals sign, it becomes the base for my logarithm. And so what does it equal now? That equals x plus y. But you guys, what did we define x to be? We defined x to be log base a of m. Log base a of m. What did we define y to be? Log base a of n. And we're done. And a lot of times in mathematics, I don't have very much room. We just put a little colored in square to kind of say, like if you look at any advanced math books, kind of shows you where the end of that proof is. Sorry if you can hear my children out there. They're wrestling with their father. I usually do these in my office, but I'm at home right now. So it'll be a little bit of background noise for you. Or sometimes we say quit and eat dinner. That's not actually what that means. I think it's Latin for, someone can comment on this. It's Latin for like, unless it's been shown or something like that. Okay, so I know you're going to feel better now because you know that this property right here, this is called the product rule, is true, and I've proven that for you. So let's look at how maybe we can use this. Make sure I'm on my layer. I'm going to do a good job today, and I'm not going to mess up with the layers. Okay, all right, so example. So let's express something like, oh, I don't know. Let's say log base 2, right, of, let's say 8 times 32 as the sum of logarithms, as a sum of logarithms, and then we'll actually evaluate it. So here's one reason that this might be useful. So I don't know about you. I mean, I can figure out what 8 times 32 is, and I could even probably figure out if I could raise 2 to a number to get whatever 8 times 32 is. But what's more important is I have this property of logarithms. I know that 2 to the third power is 8, and I know that 2 to the fifth power is 32. So if I can separate these two somehow, that's going to be easier than trying to figure out, you know, if I take 8 times 3, which is 256, I think, what is 2 to the 250? What do I raise 2 to to get 256? I don't really know. But if I use my property of logarithms, my new product rule that we're so excited about, what does my product rule say? Remember, it says that the log base a of m times n equals the log base a of m plus the log base a of n. So in this case, this is going to be log base 2 of 8 plus log base 2 of 32. And let's figure out what these are. What do I raise 2 to? Every time I laugh at that. To get 8, I raise it to the third power. Here, to what shall I raise 2 in order to get 32? I believe that's to the fifth power. 2 to the fourth is 16. So 2 to the fifth would be 32. And so look at what we get. We get 8. That's really interesting. And probably it's true. What's 8 times 32? 8 times 32, I already said it, is 256. So apparently log base 2 of 256 is 8. And that is true because that's 16 times 16. Let's look at the other way. What if we use the product rule to express as a single logarithm? And you don't always have to have, you know, a lot of times we're going to, well, not, not a lot of times in your homework, you're going to be forced to, do these exercises that might not seem useful to you. But I promise it's really just a way for you to get used to using these properties so that when we need to use them to solve an equation involving logarithms, it might be a little bit easier. Okay, so here we have log of x squared plus log of y. What base is this? Remember, this is what we call the common logarithm, and this is base 10 if there's nothing there. And really all we do here is we're going the opposite direction now. So look at, if we're going the opposite direction, so I know that, oh, I said I wasn't going to do that. If I have addition, what does the addition become? It becomes a single logarithm and it becomes multiplication. So be careful with these, because I think sometimes it's easy to think you're just going to multiply this and multiply this together. That's not true. You're going to get a single logarithm and then you're going to multiply what you're taking the logarithm of. Okay, just like with our exponents, when we add exponents, we get a single base. It's not a to the x plus a to the y, it's a to the x plus y. Same thing here. It's the log of x squared plus, or x squared times y. Okay, I hope that kind of makes sense. All right, we have a lot of rules to get to. So let's go to another rule. Whoa. Sound like my 1-year-old has started to say that. He just walks around the house going, whoa. So these rules deserve a Leo, whoa. All right, the power rule. So the power rule is an interesting rule where if we have a power, we can kind of bring it down in front. So I'm actually just going to kind of write this. So I'm going to, again, have, let's let m be greater than 0. So it's a positive number because I can't take the logarithm, remember, of a negative number. And let's let p be any real number. And of course, I know we shouldn't assume things, but a is going to be the base for a logarithm. So it's going to satisfy anything that is required of a base of a logarithm, okay? If that is all true, then, and this, I know you shouldn't have a favorite. I shouldn't have a favorite child. I'm going to wait until I see which one is the best at math to decide which one is my favorite. I'm just kidding. That was a joke. You don't have to call Child Protective Services. But of all the properties of logarithms, I don't know. I just really like this one. And what this one says is that if I have log base a of m raised to the p power, then what I can do with that p, and this is so cool to me, is that I can actually just bring that p down in front, which I think is pretty amazing. So it's a pretty neat rule, and it's one that makes things a lot easier. When you get to calculus, when you start learning logarithmic differentiation, this rule right here, man, helps so much when you're doing logarithmic differentiation. So just like before, I want you to sleep tonight. So let's do I can't spell today. Let's do a simple proof. So we're going to do the same trick. Let's let x equal log base a of m. Okay, and now the trick that we're going, so before we get there, then if I rewrite this without the logarithm, right, I'm going to bring that a over, I'm going to bring it across the equals sign, and that becomes the base for my exponent. Okay, so I know a to the x equals m. And what I'm going to do is I'm going to actually raise both sides to the power p, because that's what's going to happen over here. So we have then a to the x equals m, and if I raise both sides, right, to the power of p, we get a to the xp equals m to the p, which this implies, sometimes we can do this with proofs. Remember, we multiply exponents when we raise an exponent to an exponent, right? So this implies that a to the xp equals m to the p. So now let's go back to a logarithmic equation. Okay, so what I'm going to do now is I'm going to rewrite this as a logarithmic equation. So I'm going to take this a, I'm going to put it across the equals sign, right? And what does this give me? So this implies then that xp equals log base a, right, of mp. That a comes across the equals sign and becomes the base for my logarithm. I may have said exponent back there. The base for my logarithm of whatever's on the right side. But people, what is x? I have defined x to be log base a of m. So this guy right here becomes log base A of m, right? And it's going to be multiplied by p, but multiplication we know is commutative, so I can just put that p in front. Look at that. And that shows me that my power rule actually works. I should drop my pencil. It's like dropping your mic here when you do a proof like that, or my Surface Pen. So notice again, what did I just replace that x with? I just replaced that x with what I defined it to be, and then I just moved that p to the front because I know multiplication is commutative. Pretty easy to prove these rules. They're actually pretty awesome because you always go back to the definition of a logarithm and bringing a logarithm back to it's an exponent, people. So again, what is the rule that we have here? This is called the product rule, or power rule, excuse me, where I have rightly named because I have m to a power. Okay, so let's look at some examples of how to do these. Oh, my kids are, oh, I'm getting distracted by the loud yelling in my living room. Which is fine. So let's quick example. These are pretty easy actually to find examples for. Let's express each of the following without exponents. Okay. So in a lot of these, I'll say like I don't want any exponents, products, quotients, whatever. And that's basically just forcing you to use these properties. Okay, so what if I had like log base b of, I don't know, 4 squared, right? I don't know what base b is. It doesn't even matter. What I'm just trying to do is use this power rule. So what does the power rule tell me to do? Take that exponent, throw it in front, and then call it a day, people. So this is 2 log base b of 4. Isn't that pretty amazing? It really simplifies things. What if I had, actually, I don't want to do log. Let's bring in some natural log. What if I add the natural log of the 5th root of x? So I know I don't have an exponent here, but you kind of get what I mean, right? What is this going to be? Remember, what does it mean to take, or exponent wise, how do I take a 5th root? This would be x to the 1/5, and then I'm just going to bring that 1/5 down, and I'm left with the natural log of x. So I hope those are pretty good. I hope those make sense. Of course, you can go the other way too. You know, if I had like 7 log of y, I could rewrite that as log of y to the 7th power. Okay, so I can use this rule either way. Good. I think that's, you know, I don't want to harp on that too much because we have a bunch of other rules to get to, but I hope that makes sense. Oh my goodness. Oh my goodness. Someday I'm going to have a lecture where I don't do that. Okay, a couple more rules and then we'll be done. So the quotient rule. Actually, I think is this my last rule? I'm just gonna look at my notes really quick. I guess I should have looked at those before. Yeah, there's like 2 other like kind of interesting things we need, but this is called the quotient rule. And this is the same thing basically as the product rule, but instead of multiplying, we're going to be dividing. So again, same thing, let m and n be positive numbers and a be any base. Now I'm getting lazy. We're to the point in the lecture where I'm starting to get lazy. Oh, I meant to erase that. All right, so what should we do if we have log base a of m divided by n? Well, remember, what do we do with exponents when we divide them with like bases? We subtract them, right? So what does this become now? It doesn't become log of m minus n. Be careful there. It becomes log base a of m minus log base a of n. So again, it goes from a single logarithm to 2 logarithms. And the proof of that, I'm gonna just omit for time-wise. You prove it exactly the same as we prove the product rule, except when you take that m times n, instead of doing the m times n, you do m divided by n. I'm sure all of you will go and look through that. Your book also gives an interesting rule of it where you take n to the -1 power, but you know, that's up to you. So quick example, let's express as a difference of logarithms. I'm just going to put logs because I'm lazy. So what if we had something like, log, let's say base 4 of y over 16. Okay, log base 4 of y over 16. So if I'm going to use my quotient rule right here, okay, that tells me it becomes the difference of two logarithms. So this becomes log base 4 of y minus log base 4 of 16. And you know that any mathematician or any math teacher out there needs everything simplified. You probably have nightmares about, math teachers saying, "Did it simplify? Simplify." So we can simplify this guy right here. Look at what this is asking. This is asking, to what shall I raise 4 in order to get 16? What exponent do I give 4 in order to get 16? Well, I would square 4 in order to get 16, so that is 2. So this logarithm right here actually equals this difference right there. Likewise, I can go the other way with this. I can express as a single logarithm. All right, and so to express as a single logarithm, basically, I don't know why I put an A there if we weren't gonna do, it doesn't really matter, another one. But what if we had something like, I don't know, let's say log base 3 of like 54, right, minus log base 3 of 6. These are always kind of interesting ones. So I have log base 3 of 54, which I can't, I don't know a number off the top of my head that when I raise 3 to it, I get 54. I know it's not going to be a whole number. And I don't know a number off the top of my head that when I raise 3 to it, I get 6. But look at what I do know. I do know that if I take log base 3, so remember this becomes a single logarithm. I'm subtracting two logs, quotient rule tells me that it becomes a single logarithm. I'm going this way now. I'm going to have 54 over 6. I believe 54 divided by 6 is 9. I'm pretty sure. Sometimes my multiplication facts aren't always the best thing ever. But I'm pretty sure that's 6. Yeah, 27 plus 27. Yeah. So look again here. Apparently I'm obsessed with 2 today. But what do I raise 3 to in order to get 9? I get 2. So actually this whole thing just equals 2. Okay, so be really careful with these. I kind of hinted at some of the common mistakes that people make with the quotient and the product and the power rule. Let's do a couple more examples of kind of putting all these rules together, okay? So what I want to do first, let's do a couple examples of putting these rules together. I want us to express as a sum, express as sums and differences of logarithms. And what I want here, I'm going to be very specific here. I don't want any products. I don't want any products that I could simplify, right? Using the product, quotient, or power rule. I don't want any powers. I want you to basically take this sucker and I want you to expand it out as much as you possibly can. Using your properties, okay? So let's look at something like this. Log of x squared y to the 5th all over z to the 6th. So what I'm going to use first is I'm going to use the quotient rule because I have a quotient, right? So what my quotient rule says is I can take the log of the numerator and I'm going to subtract the log of the denominator, okay? Now, I know you want to start bringing down these exponents. I want to do it too. We can bring down this exponent, the 6 down. That is no problem. But here, I can't bring the 2 down or I can't bring the 5 down yet. Because remember, when you bring that 2 down, you're saying that everything is being squared, okay? That you're taking the logarithm of. So what we actually have to do here first is I have to break up this term. Oh, poor guys. I have to break them apart. And I'm going to use the product rule to do that. I know that the common mistake, you guys. Look at what I just did. This is a common mistake. See how I accidentally didn't bring the log with me? And I was going to make this something like log of x squared plus y. Don't do that. Don't you dare do that. Okay, that's not what the product rule says. It says that the log of a product is the sum of the logarithms. So I'm going to take log of x squared plus log of y to the fifth. I could bring that 6 down right now because I can't really do anything else with z to the sixth. And now my final answer, if I get this all nice and tidy and pretty, I'm going to get 2 log of x, bring that exponent down using my power rule, and then 6 log of z. And that is completely expanded as much as I can go. Okay, I hope that kind of makes sense. What if we had something like this? Oh, this is a doozy. Log base 4 of the cube root, okay, of a squared b all over c to the fifth. That is a good one. Now there are a couple ways that you can do this one. But what I think is the easiest is I want to use my power rule as much as I can. So I'm going to rewrite this as log base 4 of a squared b all over c to the fifth, all raised to the 1/3. Now because all of this is being raised to the 1/3, I can bring that 1/3 in front. Now, the other thing you could do, and this would be mathematically valid, is you could distribute that 1/3 to each of the exponents and, have a to the 2/3, b to the 1/3, c to the 5/3, and then bring everything down. But I'm not going to do that. So I bring the 1/3 down first. I'm going to get this guy right here, log of a squared b all over c to the fifth. Let's make sure this is all different. And then what am I going to do here? I'm going to do exactly what I did up here, and I'm going to separate these guys using the quotient rule. But I'm going to be very careful to put parentheses because I know that when I multiply more than one term, what am I doing? I have to put parentheses. So remember that 1/3 is being multiplied by that whole logarithm. And now look at, I'm changing that logarithm into more than one term. So this becomes log of a squared plus b minus log base 4, of c to the fifth. Does everybody see that? I'm going to pretend like you people out in the space of the internet are telling me, yes, Sarah, I totally understand what you're doing. Let me get us some room here, people. Okay, so what else? Let's see. Let's see. So what else can I do to this? So I still have the 1/3 out front, and then I hope this is going to be okay, but I'm kind of break these apart, and I am going to bring the power rule down at the same time. So I have log base 4 of b, and then minus 5 log base 4 of c. And now you could leave it like that, or if you have a hankering to take that 1/3 through, you could do 2/3 log base 4 of a plus 1/3 log base 4 of b minus 5/3 log base 4 of c. And you know, guys, as you start doing these and getting more familiar with it, a lot of you actually could probably go from this step straight to that step, and that is fine. Just be careful. Make sure you bring everything, down correctly, and you break them apart correctly. That would be fine, but just be mindful that what am I trying to say? Be mindful that you have to bring the exponents down, and that 1/3 you can take through and has to multiply times the whole thing and not just that first term. Let's do one more example where we might have something. This is part C, I believe I want to do. So part C, what if we had, actually, you know what? Sometimes when I get sick of doing examples and writing log all the time, I just bring in a natural log because there's only one of those. So I'm pretty excited to do something like that. What if we had something, I don't know, like this? X squared e to the 4th all over y z cubed. All right, let's see what happens. Again, I'm going to break this apart because it's quotient. Sorry, I'm doing all quotients, but they're kind of more interesting. X squared e to the 4th, natural log of x squared e to the 4th, then minus, again, another natural log of yz cubed. And now notice I have products right here. So I'm going to break up these products using what? I'm going to break them up using addition. Okay, Remembering again, it's not the natural log of x squared e to the plus e to the fourth. It's the natural log of x squared plus the natural log of e to the fourth. And now here's where people always make mistakes. All right, you guys, you are subtracting more than one term. So when you subtract more than one term, thou shalt put parentheses. The math gods say you must put parentheses. Look, I'm not putting it right now, and they're going to smite me down. I'm not putting it right now. Look at what you're saying then if you don't put parentheses. You're saying you're subtracting y. That means that guy's going to go in the denominator if you were to go backwards. But then that plus sign means you're multiplying. We know the z cubed needs to stay in the denominator. So we're actually dividing by that whole thing. So you must put parentheses. And then we can put the parentheses through. Guys, look at what this is asking. What do I raise e to in order to get e to the fourth? People, you raise it to the fourth power. Don't overthink that one. Remember, natural log is base e. So what do I raise e to get e to the fourth? You raise it to the fourth. Minus the natural log of y. I'm going to take my negative through, and I am using the power rule to bring down all of my exponents. Easy peasy. So that's going to be like one way we practice using these properties in this section is taking a single logarithm and expanding it out as much as we possibly can using our properties, because why not? Why wouldn't you do that once you know all your properties? But now let's look at what if we are given this huge long expansion. So by the way, expanding those, super useful when you get to calculus to do logarithmic differentiation. If you have like a pretty complicated logarithm you want to take the derivative of, eventually you'll see it's way easier to expand it out. However, on the other side, sometimes it's easier to get it to be a single logarithm if you want to solve an equation that involves logarithms and if you want to simplify some stuff. Oh, whoa, I don't know what I just did there. Sorry about that. Okay, so our next example is going to be going backwards with our rules and expressing as a single logarithm, okay? So we'll do a couple of these, and then I think I have like one more rule to give you, and then we'll kind of tie it all together, and then we'll call her a day. So let's look at a simple example here. 5 natural log of x minus natural log of y, okay, plus, I don't know, 1/3 natural log of z. Okay, so first, before we can actually put these together as a plus, you must have a 1 in front of the logarithm. So what I'm going to do first is we're going to kind of go the opposite way as we were just doing. Remember on all those, the power rule kind of came at the end? Well, now when we're going backwards, we're going to have that power rule go at the beginning. So this is z to the 1/3. Once I have it in that form, once I get 1s in front of all of the natural logs, now I'm able to use my rules here. So what does this become? The subtraction becomes a single logarithm, okay, of x to the 5th over y. And now I have plus the natural log of z to the 1/3. Now that I have addition, what does that addition become? It becomes multiplication. When I multiply this, think of this as z to the 1/3 over 1. Remember, when you multiply fractions, it's the easiest thing we do. So z to the 1/3 is the cube root of z. I just multiply it on the top all over y. Notice how I have a single logarithm. I don't have like a logarithm divided by another logarithm. I have a single logarithm. Oh, I forgot my 5th. X to the 5th, right? Correct. X to the 5th cube root of z all over y. Okay, single logarithm by bringing those together, kind of the opposite direction of what we did in those last ones. I'm doing a good job now with the layers. Let's do part B. Let's do another one. Let's do one that's kind of fun, just fun to do because we're mathematicians. I don't know, log base 7, let's say, and mathematicians like to do things like this. 4x squared minus 1 minus log base 7 of 2x plus 1, let's say. So this is a simple one, and this one is just kind of fun because some factoring comes in. I know that our definitions of fun, I've said this before, probably vary. But what does the subtraction mean? It means I use the quotient rule and it becomes division. And now because, you know, a mathematician can't sleep at night if they know that there is a factored form out there with a common factor that can cancel. This is a difference of squares. 2x plus 1, 2x minus 1. I have 2x plus 1 on the bottom. Those suckers are going to cancel. And what do I get? Log base 7, my final answer, of 2x minus 1. So that was kind of just, I think, kind of a fun one to do. So I hope those kind of make sense. I mean, we can get even more complicated here. You know, we could have, you know, log base 6 of, I don't know, x minus 3 log base 6 of y minus 2 log base 6 of z plus 1, let's say, something like this. So one like this, again, we're going to get rid of our exponents. So I'm going to have log base 6 of x, or excuse me, not rid of our exponents. We're actually going to bring back our exponents so that we can have ones in front of everything. Minus log base 6 of z plus 1 squared. Okay, I'm going to go left to right again. What does subtraction become? Subtraction becomes division. So I get x over y cubed, okay, minus log base 6 of z plus 1. What is z plus 1 squared? Again, what does subtraction mean? It means division. Where is that guy going to go? Well, it's definitely not going in the numerator, you guys. That would be multiplication. So where does it go? It must go in the denominator because it's division. So my final answer then is x over y, or log base 6 of x over y cubed times z plus 1 squared. Okay, I hope those kind of make sense. They can kind of take a while to get used to, but that's why you just have to, practice. That's what you do with any of this stuff, right? It's just practice. All right, two more. What I want to do here is I just want to write down all of the properties, and I'm actually going to add 2 properties to my list, and I'll kind of talk about them, but I want to add them and kind of show you what they mean. Properties. I think that's how you spell properties. I'm pretty sure. Okay, so first one, log base a of m times n. And remember, these go either way. You can use them either way. You don't have to go left to right. You can go right to left. So again, this is the product rule. Okay, what else do we have? We have the power rule. So log base a of m to the p power is p times log base a of m. Remember, we can bring that exponent down. 3, if I divide log base a of m divided by n, what does that become? The quotient rule tells us it becomes subtraction. Remember, these are all exponents, so this should make sense. Well, maybe. Log base a of m minus log base a of n. Okay, and now I have a couple here that I want to add to this. So one is, if I have log base a of a to the x, think about what this is asking. What should I raise a to in order to get a to the x? We actually saw this earlier when I said natural log of e to the 4th is 4. Remember, what is natural log? That's log base e of e to the 4th equals 4. That makes sense because what I'm asking is, what do I raise e to get e to the 4th? Well, you would raise it to the 4th. So in this case, look at what this is asking. What do I raise a to in order to get a to the x? Well, you would raise a to the x to get a to the x. Okay, I hope that makes sense. Now, this one isn't quite as intuitive, but if I have a and I raise it to log base a of x equals, what this is going to do too is this is going to kind of undo each other. Now, let me tell you why this is true. Remember, you guys, that a to the x and log base a of x, guys, these are inverse functions of each other. Remember what we know about inverse functions? That when we compose them, right, they undo each other, you guys. So these last 2 properties actually are just properties of inverse functions. So look at, if I compose these functions, so if I take this guy and for the x, I actually plug this guy into the x, what do I know? They're going to undo each other. So really, these last 2 are just properties of inverses. I hope that kind of makes sense. These should be pretty simple. You know, if I have log base, I don't know, 14 of 14 to the y, this guy is just going to equal y. They're going to undo each other. If I have 14 raised to the log base 14 of y, these guys again are going to undo each other. These properties right here are going to be super useful when we are solving logarithmic equations. All right, I should probably go eat dinner with my family. So I'm going to let you go here. I hope this all makes sense. As usual, if you have any questions, let me know.